Okay, so let's move to a different potential, one that is always finite. So let's say it has a value V naught for negative values of the position x. We'll have V equal to 0 between 0 and L, where we previously had the one-dimensional, where the particle was forced to live in the 1D prison. Now we will see that we will allow it, by changing these values, to leak out of this region. So this is for x greater than L. And so let's look at the Schrodinger equation, right? So the Schrodinger equation, or the time-independent part of the Schrodinger equation, which looks like this, where this is the x part. This is equal to, we have a potential here, plus V psi of x is equal to the energy times psi of x. And so we have that the second derivative of psi and x is equal to 2m over h bar squared times the potential minus e times psi of x. And so we can see that maybe we can let's draw the potential. So this is x, and we want to draw the potential in green, V of x. And so if this is x equals 0, and this is x equals L, we have, let's say this is V naught. So here we're at V naught as well. And then here we come down to 0. And so it looks like that. So in the region between 0 and L, what we have is this is equal to 0, and so we have a function that we've seen before, right? Two derivatives of psi in x is proportional to a negative number times the function itself. We know how to solve that. That's a sine function. That's similar to what we saw before, or exactly what we had before. But now the function doesn't go to 0 here and here at these boundaries. So what does the solution look like here and here? Well, we have v minus e, and so we have to consider the value of e. So what's the value of e? Well, let's consider a value of e such that, let's say, the energy E is lower than the potential. So E is lower than V. If that's the case, then what we have is this becomes positive. And so we flip the sign, right? The coefficient is different, but the important thing is that it's a positive number. And so two derivatives of psi with respect to x proportional to psi of x, the solution there is exponential decay. And so if we want to look at this, let's say we plot some psi function. So this is, say, x equals 0 and x equals L. And we're looking at the lowest, so the psi 1 of x. Then we know that the greater we make v naught, if we make v naught go to infinity, then the function has to just look like functions that we saw before, right? Just one bump that looks like this, but now the function can have non-zero values here, so presumably, and it's going to have to be symmetric, so it's going to look something like that, and then here we're going to have some solution. The question is it going to be like this or like that? And exponential decay, right? So exponential decay, it could look like that, or it could look like that. So we'll be a little bit more precise about why it has to look like that. We'll see this. First of all, the bending has to be the opposite here because it's a flip in sign. And then we also have to ensure that it's normalizable, so we're not going to choose an exponential growth on either side, despite the fact that such solutions obey the Schrodinger equation.